Welcome back. So let's continue. As a follow-up to some of the questions during the break, let me again comment on what's going on here. It's very important to understand what's going on. Each one of these little squares here is an item. It can be a value, it can be a key value, right? It's these whatevers that I told you about. In that case, of course, for slides, I was not going to put billions of them, right? But here we have 3, 3, and so on. This is every time a value. Now, you need to understand what's going on in the thread. This is a thread on core 1. It's basically taken this value, computing this, computing that, and this is the output. Then it's going to the next one in the thread, taking this value, calling a function, this is the output. Then the third one, done with task 1, gets a new task, task 5, and again, sequentially, takes the next item, goes down, blah. Takes the next item, chain of function calls, blah, and so on. So you see there is an input and an output. The next thing that is important to understand is that there is this intermediate RDD right there, right? With all of these intermediate values that is neither the input nor the output of the stage, right? It's an intermediate RDD. It appears on the data flow diagram, right? If I draw the DAG of RDDs, that will be one of these RDDs. But on the physical layer, this RDD is purely virtual. It never ever exists anywhere. There is not even here, you could think there is a list of these 3 values somewhere. No, not even that. These values are just transients. They are computed on the fly, all on the way between the input and the output, then forgotten about. So once you've computing the green value, this value here might have been on a CPU register temporarily, then it's gone. So what's important to understand is that this first RDD here might exist, you know, as a local list for task 1, a local list for task 5. This output RDD might exist in the sense that there is a list of these output values, but the one in the middle never ever exists. It's purely virtual, it's purely logical, right? It's only in your imagination. Yes? Yep. Absolutely. So you need to recompute all over again from the blue one. In reality, it might be worse than that. You might have a series of 10 transformations, but not in a single stage. Let's say you have 5 stages, right? 5 stages, and maybe you fail in stage 4. And bad luck, you lost the values all the way to stage 2. Then you need to start all over again from stage 2. Right? So sometimes you can be thrown back a few hours back just because something failed. It all depends whether you threw away the values or not, if you lost them or not. I haven't told you how we can have multiple stages. This is still coming. Right now, we are still in a single stage. All right? There is a word for that. Remember that word. It's called materialization, materialized. We say that the RDD here, the input RDD, is materialized in the sense that it exists as a distributed set of lists all over the cluster. Every node, there is a list of these values. It is materialized. The output is materialized because at some point you're done with the computation and you have all of these values. It's materialized. And the intermediate RDD here is never materialized. It's in your imagination, but it never exists as in any form of structure in the cluster. For whom is that clear? Right. This is called materialization. Okay. Very good. So you see why it's efficient. This is precisely because we don't materialize the orange one that we are fast. Materialization is expensive. It's expensive in space, it's expensive in time, you know, it's very expensive. So the reason why it's efficient to execute stages like that by squeezing the transformations together is because we materialize less RDDs. We kind of pass over some of the RDDs to directly compute and materialize later. Okay. Now you can control a few things nicely over the command line if you actually try it with the Spark submit command. So you have the Spark shell where you can directly work on, but typically what users do is they create a Java jar and then they use Spark submit to send it over the cluster. You can do the same with Python, with Scala, it doesn't matter. What's nice is that you can supply parameters to this submission of your Spark job. you can specify the number of executors, for example, you know, how many you want here. You can say, I want 42 executors. That's going to be the yarn containers, right? So 42 executors. You can even specify how many cores you want per executor. You can say, I want each executor to have 2 cores, right? Exactly like here, actually. This is 2 cores per executor. And you can also say how much memory every executor, not every core, every executor is going to have. So here you're saying 5 gigabytes, right? So you can actually compute the resources you're using. If we have 42 executors of 2 cores, then we have 84 cores in total. And if we have 42 executors with each 5 gigabytes of memory, then we have 210 gigabytes of memory that we need. So of course, when you specify these parameters, you really need to sit somewhere and do some math on a napkin or whatever, right? So you need to look at the machines you have, how many cores do I have on the machines, how much memory do I have, and then you need to come up with these parameters in a way, you can use them together, that it's efficiently using your cluster. All right? And you could have, of course, imagine that each machine has 8 cores. Then you're going to have 4 executors on each machine, right? The cores are basically grouped in a 2 times 4 fashion on every machine. Yes, there is a question over there. Where's the catch box? Oh, it's already there.
Is it possible to also specify how many slots we create in MapReduce?
Yes. So in MapReduce, you have control over the number of slots that you want.
But not the number of nodes actually doing
things. The number of nodes you have control of when you build your data center or when you provision your machines, right? It basically depends if you're version 1 or 2. If you have version 1, it's a physical constraint in version 1. In version 2, this is what you get over yarn. So then you can decide over yarn, I want all of these containers. But then you're not going to think in terms of machines. You're going to think in terms of containers, right? Because there might be 100 people using the same cluster. It doesn't matter to you if you have 2 containers on the same machine or different machines, right? It doesn't change anything to the execution, right? So this is why you are one level of abstraction higher than the machine with this virtualized environment with the containers. Right? Did I answer your question? Awesome, thank you. All right, so you can control all of that. In the newer versions, there's even some dynamic allocation that it can even figure out how many executors it allocates for you if you prefer. So a lot of things have been improved since then. Okay, and now this is the spaghetti. This is called the wide dependency. You can see that this is very different from this, right? This is a narrow dependency we can parallelize. As you can imagine, this is much harder to parallelize. In fact, you can't. This is going to trigger what? A shuffle, exactly. This is triggering a shuffle. This is the quadratic thing, where the data flows all over the place, very inefficient. You have no choice. You have to send the data over the network, and then this is just like the shuffle phase of MapReduce, where every destination container contacts every sender container and the data is transferred. All right, so this is the big spaghetti in the middle. What happens is that you get a new stage, right? You had a stage that ends, then you shuffle, and then you get a new stage. So you see that this notion of stage is like the phases of MapReduce. You have the map phase, then you shuffle, then you have the reduce phase. Here, you have a stage, you shuffle, you have a stage, you shuffle, you have a stage, you shuffle. You need to shuffle every time that you have a transformation like this. Who can give me an example of transformation that is like this? Join, yes, absolutely. A join is going to trigger a shuffle. Another one? Sort, yes, absolutely. That's another example. Another one? Group by, yes, exactly. That's exactly the idea. So sorting, grouping, joining, these triggers shuffles. What about not triggering a shuffle? What are the narrow dependency examples, a few of them? Map, yes, that's one. Another one? Flat map, yes, that's true as well. I also hear the correct answer here. Filter, right? Filter is also one. Filter is indeed a narrow dependency, right? So this should give you an intuition, right? Filter, map, flat map, narrow dependency, join, sort, group by white dependency. So you really have to, without thinking, this has to be an automatic thought. If I say grouping, sorting, joining, you have to think shuffle. This is going to shuffle. Okay. Filter, map, flat map, this can all be squeezed in a single stage without any shuffling. So what's going to happen is pretty much like this. You have a stage, you shuffle, you have a stage, you shuffle, you have a stage, you shuffle. But unlike MapReduce, you can do it 10 times, 100 times, as many times as you want. So you see, we have an additional level of sequential, right? We have a sequence of stages, and within each stage, things are happening in parallel, and in between stages, the data gets shuffled all over the place, right? So this is what's happening on your cluster, basically. It's an alternating between shuffling and stages. Okay, now in the case of join, it's not quite linear. It might be that you have something more complex. Like in that case, you have 2 stages for the 2 sides of the join, then you shuffle, then you have a third stage, and so on. You have a question? Yeah, over there.
So my question is, for each stage that is like, for example, to get the input, stage 3 to get an input, this means that stage 1 and stage 2 have to actually materialize their output. They have to write it on disk, right?
On disk, for example, can be in memory, can be on disk. Yeah.
Okay, but they do have to write. It's
yes,
no longer that we can just.
You do have to materialize. Yeah. Shuffling forces you to materialize anyway. From the moment you shuffle, the data is materialized. Because if you don't materialize, then you have nothing to shuffle, right? So this is the idea. Yes, you have a question too?
But we can just read from memory, right? When we go from one stage to another.
Sorry, I didn't understand.
We can read from memory, right? When we go stage 2 to stage 3. Have to spill to this.
Oh, so yes, indeed, it doesn't have to be spilled to disk always. It's something you can control. In fact, this is called pinning. You can pin your RDDs in the sense that you can say, please keep it in memory, please keep it on disk. If you're really paranoid, please keep it both in memory and on disk, and that way it's preserved. In fact, when you do that, it even preserves it even for later. So you might be at stage 10, and you still have the RDD, for example, at the output of stage 2. You can really keep it if you want. Did I answer your question? Okay. Any other questions? Okay. Let's continue then. So now this is a summary to not confuse things because there are several words in there. So we saw that when you have narrow dependency transformations, you can squeeze them into a stage without shuffling in between, and then you don't materialize the intermediate RDDs, right? Only the input and final output of the stage. The stages, so this is like a vertical grouping, but the stages are split in tasks, just like MapReduce, right? So you have 2 ways of looking at a stage. You can view it as a logical sequence of transformation, logical, or you can see it as a physical set of tasks. This is physical, this is logical. Here, a sequence of stages is a job, right? Stage shuffle, stage shuffle, stage shuffle, then you get your job. Okay. For whom is that clear? Okay. Otherwise, you can also read the textbook and so on, and don't hesitate to ask more questions. Now there's a few things we can tweak in performance, and in fact, now I already partially answered that, but imagine you have this DAG of RDD. So this is a logical thing here. It's a logical DAG of RDDs that gives you the transformation calls. Each transformation corresponds to an arrow. And we have an action here that triggers these computations. Then we have another action that triggers these computations. Then we have another action that triggers this computation. There were 3 jobs here. But do you notice? We did 3 times the same thing. So what you do in practice is that you can request pinning here. You pin the results the first time of this RDD here. You keep it materialized. You can even force it to be spilled on disk and preserved on disk if you want. And then you can directly start from here for the subsequent actions. You don't need to recompute all of that, except if there is a failure and you lose data and so on, then you have to retrigger all the computations all the way there. But as long as you don't lose the materialization of that RDD right there, then you can be more efficient. For whom is that clear? Yeah, it's just preserving the intermediate data. Another optimization you can do is that when you have a white dependency, you might, let me put it that way for a start, you might be lucky. Imagine that you want to group your data, and it so happens that all the keys that are the same are already on the same machines. You're so lucky that this is the case. Then you don't need to shuffle, right? You are lucky. It's already there. The keys are already together on the right machines. But in fact, you can actually push your luck by pre-partitioning yourself. You can actually instruct Spark to reorganize. It's going to cause a shuffle just once. You can reorganize your data to partition it in a very specific way that you know that you might have several shuffles later that will not happen because of the way you took care of putting the right keys on the right machines. This is called pre-partitioning, and it can also save you some efforts, because here it means that you can squeeze these things in stages just like you do with narrow dependencies, right? For example, you could pre-partition the data. You could even do that already from the in a very early phase when you read it from disk. And then you don't need here to shuffle. It's an optimized join. You just need to here to shuffle around, send the data over there. But this here doesn't require a shuffle. So it saves network bandwidth, saves you time. Okay. So far, so good. Let's go to the data frames. Yes, there's a question.
So on this example, one thing that's unclear to me is we said that stages are computed sequentially, right?
Yes. Mm-hmm.
So in this case, let's say that one is stage 1 and that one is stage 2. Do we know? I mean, in my head, I know that stage 1 will be executed first, then stage 2 comes.
Mm-hmm.
And now I know that their outputs have to be joined together. How does that actually work? Like, yeah, my problem stems from in this diagram, actually, if I think about it as them being a stage 3, essentially, depending on stage 1 and stage 2.
Logically, yes.
Sorry?
On the logical level, yes.
Okay, so there's a logical representation done beforehand that sort of knows about these dependencies between stages, or?
Yes, so basically what happens here, it's really a pedagogical thing, right? So this is a plan, like a master plan to execute your job. And in this master plan, it's basically starting with the DAG, the DAG that you had here, but you group them into the stages. So whenever you know there's narrow transformations, you group them in stages, and then you look at specifically the shuffles. So it's basically the same diagram as here, except that you did this grouping in stages and you explicitized the shuffling, right? Then what's happening is indeed, it can be, it doesn't have to be, but in a typical case, you indeed first do stage 1, then you might keep the RDD, it's there. Then you do stage 2, keeping the first RDD of stage 1. And then you have, on the machines, you have RDD1 and RDD2. Then you shuffle, so the RDD1 is shuffled around. In that case, RDD2 doesn't need to. Then you go to stage 3. However, I think it might be possible to, I'm not entirely sure, but I think it might be possible to also split your cluster in 2 and say these machines do stage 1 while these machines do stage 2 with the Spark scheduler. I'm not entirely sure, but I wouldn't exclude the possibility. At least there's a theoretical possibility of that you can also decide to do things that way.
So in that case, could we assume that there could be an optimization where stages that are not dependent on each other could be executed in parallel, like in this case?
Yes, exactly. Yeah, because it's a DAG, right?
Yes.
So when you have a DAG, what is, I was about to say space-like separated for whoever that makes sense, thinking of special relativity. So whenever you don't have any arrows, for example, in here, you could execute this, then this, then this, then this, or this, then this, then this, then this. It doesn't matter, right? All you need, it's like a dependency graph, right? That you probably saw in theoretical computer science. You need to organize in a linear fashion in a way that preserves the arrows. This is called a linearization of a DAG. It's a list of nodes of a DAG such that the order of the nodes in the list is compatible with the arrows of the DAG. That's called the linearization, right? But you don't linearize the DAG itself. What you linearize is the stage DAG, right, after the grouping. Does it make sense? Okay. I hope I didn't scare you with linearization and all these things. This is just the terminology used in DAGs. All right. Okay. Any other questions before I move on to data frames? This is a super cool part of the data frames. This is really a huge improvement that was done in a subsequent version of Spark. So here it goes. RDDs are very generic. You can take any value. You can have transformations that manipulate the values, but the values can be absolutely anything. In fact, because of polymorphism, it can be literally anything. It can even be a huge mess. You could even have I don't know, if you push it, an RDD of objects, and then you can have integers and strings and whatever, and yeah, it's as powerful. But this is slow, of course. And this, we are going back to the question that one of you asked earlier: how can we improve the performance there? Well, there is another problem. So the first thing is that it's inefficient, because we can do much better than that in the case that the data is structured. The second problem is this. This is Python code in order to open a text file, and then you apply a filter, a map. By the way, these are narrow dependencies, so this will be the same stage. Then you have reduce by key that's going to shuffle the data around, and then you have a take action. But now this is JSON. Do you see a difference? I don't. The reason is Spark and Python don't care about JSON. No, more precisely, Spark doesn't care about JSON. JSON is just an object like any other. Right. So if you open, it has to be as a text file. You see, it's a dataset.json, but you have to open it as a text file. And then you have to use the Python library to parse the JSON file into a Python dict. So you're really working with Python here. Spark doesn't even care. So what you have here in RDD2, it's basically an RDD of Python dicts. It's an RDD of objects, of Python dicts. An RDD of maps, if you speak Java. And you see that the syntax here that is used is basically Python syntax. This is in Python, how you access an object, and so on and so on. We are lucky that it's Python, because the same thing in Java, you can imagine the complexity of the code, right? It's because Python is kind of JSON friendly that it works nicely. But you see the extra work, all the verbosity, we have Lambda function, we needed to manually trigger the parsing of the JSON. That's very low level, right? That's a lot to think of when you actually have to query the data. Then you have to create a pair, count by key, and so on. So yeah, okay. This is not good. You're basically asking a lot from the user, and writing code like that requires a lot of training in order to even understand what it does. This gives me headaches when I look at this code, right? You need to understand what an RDD is. You need to understand the transformations. You need to know the transformation. You need to understand what a lambda is. You need to understand the Python dicts. You need to understand all of this Python syntax for the dicts. So this is, you need to know so many things to make something like that work. Enter data frames, which are basically RDDs of rows. It's specific RDDs of rows, where every item, every whatever in my RDD is a row. And the rows, as you can imagine, are like data frame rows. They have the same schema. They all have the same columns, right? Data set row is what you see in Java. When you create a data frame in Java, you actually write down data set row with a generic as a template. Okay, so once you have seen that it's an RDD of rows, you probably now realize that an RDD of rows is just, let's assume the rows are flat. An RDD of flat rows is a table. Who sees that? Because remember, an RDD is a collection of whatever. So we have a collection of rows, and a collection of rows with the same schema. These are tables. So you see that this is the better abstraction. I understand tables. This gives me less headaches than having to think of RDDs or whatever, right? So it's less headaches. What's more, when you store the tables, and more generally data frames, because we'll see we'll allow for nestedness just like we did for a few weeks ago, you can store it efficiently. In fact, you've read the Dremel paper. Who read the Dremel paper? Right, so you see how you can actually store column-wise things. And storing column-wise is absolutely excellent for performance. Why? Because you only look at the columns you need. Imagine that I have a query that only needs these 2 columns, and I don't need these 3. Then I just ignore these 3 and only read here. My I/O, my input/output, the data that gets read from the disk and the data sent over the network is much smaller than if I read everything. If you use RDDs, you can't do that. You have to read everything, right? So this is another improvement. And finally, and this is the question you asked earlier, data frames take less memory, because you can indeed, since it's homogeneous, for example, imagine a column with only integers, or an RDD of objects that always have the same 3 keys, then you don't need to repeat the keys. It's just your schema. So this is something that is not new. It should not be new because I explained to you the Parquet binary format that is used to store valid JSON. When your data is valid, has a structure, and every one of your items has exactly the same structure, then you can squeeze it in a binary form that is much, much more compact than in a raw form. For whom is it then natural that data frames take less space? Imagine, for example, let me give you an example, a sequence of 1 billion JSON objects that have a key foo that is an integer and a key bar that is a date. If you don't know this schema, you will have to store, for example, an RDD of strings, and then you create dicts and so on, right? But foo and bar are literally stored 1 billion times. Every time, every JSON object has a copy of the foo string and the bar string. But you can do better than that because you can think of that as a table with 2 columns, a column foo, a column bar. The first column is just integers, the second column is dates. And since you store it column-wise, what is your column of integer? It's just a sequence of integer. There is nothing simpler than that. It's just plenty of bytes, 32-bit for every int. Let's say these are ints. You have 4 bytes, 4 bytes, 4 bytes, 4 bytes. You literally just concatenate the ints one after the other. This is as compressed as it gets, right? And the same for the dates. In case you can even count the number of days. You can even store the date efficiently without actually storing the year, the month, and the day. So this is why data frames are much more compact and less memory consuming. Who gets it now? This intuitively? Okay, awesome. So now the next super cool thing that you get with data frames is that you can forget about the transformations and actions and so on. All you need to do is write SQL. It's back, Spark SQL. So there's many dialects of SQL. It's like Swiss German. So this is Spark SQL, but you recognize it. We had the brush up. Now you understand why we had the brush up in the first week of the semester. Select from where. It's good old SQL. All right, so that's great news actually, because you already know SQL, right? So you can actually just go ahead and query data frames. The only thing you need to understand is that you can read like this data, like directly JSON. It's directly going to guess the schema. If you do that, then you create a view data set, like a relational table, and then you write down your SQL. You have this .SQL call where you put the SQL in there. Then you can collect the output. Of course, I could also have put limit 10 and then collect, right? It would have been the same. Okay. Now, what is important to understand, but this is also what we did a few weeks ago, if I take a CSV file, I can open it as a data frame, right? This is very natural to do. Here, I have a JSON file. It's valid JSON, right? In the sense that I can validate it against foo, integer, bar, boolean, for example. And I can make a data frame out of that. In fact, Spark does it automatically. You don't even need to worry about the schema. Spark can automatically try to infer the schema and give you the data frame over there where it detects that foo is an integer and bar a boolean. You can see that this takes less space on the right than on the left, because here you have 7 times foo and 7 times bar repeated all over the place, right? Okay. For those who really cannot have enough of transformations and chaining function calls in Python, you can still use this syntax. It's equivalent. You can either do the SQL syntax or you can do the chaining of transformations, but these are data frame transformations, not RDD transformations. Yes?
Isn't there a mistake here? Because it should be df, isn't it df2 that should be on df3 and df3 that should be on df4? Because we
Oh yeah, you're correct. Yes. Yeah, I will fix that. It should be df, df2, df3. Of course, it would also work, right? You could also take df every time, but that probably doesn't make sense. Yeah, thank you for that. This is something I'll fix. Yeah. Okay. Just as a poll, can you raise your hand also on Zoom if you prefer this to SQL? Who prefers this? Some of you on Zoom. Some people prefer. How many raised hands? 2. Okay. Now, who prefers this? Wow, you see it's more popular. It's much simpler, right? Much more simple. Okay. And 3, do we have more? Still a chance to raise more hands? Who on Zoom likes SQL? It's more popular in the lecture hall then. Yeah, there's a correlation here between lecture hall zoom and SQL transformations. Okay, thank you very much.
There's one question on Zoom.
Yep.
If a schema is schema modified by Spark automatically if we use UDFs and change data type?
You can specify the schema, and in that case, Spark is not going to infer it. So you can tell Spark what your expected schema is, and then it's actually going to be faster if you give the schema. Yeah, but I'm not sure if that was the question. Was it your question? Not exactly. Can you reformulate?
Yeah.
If I see it in written. Oh, UDFs in the sense of user-defined functions. I need to think about that. So first, I need to explain a user-defined function is basically the lambda, right? When you have a lambda and you put your own function in there. I will get back to you offline. I don't exactly understand what you mean with changing the schema. Let's take it offline, right? And then we'll make sure to answer that. Right? Can you make sure to write the name and then we'll get back? Okay. Okay. So we have established that at least in the lecture hall, SQL is more popular than the chain of transformations. But you know, it's just a matter of taste. Some people prefer this, some people prefer that, and both are equally performant. So it's both are okay. Yes? Yes, I think I can't remember if it's Python or Scala or Java, but it's basically automatically, at least let me put it that way. There exists a language where you can just concatenate strings like that and it automatically assumes a concatenation. I just cannot remember if Python, who knows if Python does it? Python does, okay, so this is correct. So this is Python. And indeed, when you do that, it's automatically chaining. Otherwise, imagine the nightmare to have this multi-line SQL like that. All right. Okay. Good. Now, these are the types that you have in data frames because this is a schema, right? So you need types. Remember what we did a few weeks ago. You already have the framework for all of that. So in particular, we have atomic types, byte, short, integer, long, float, double decimal, strings, booleans, binary, timestamps, dates, and we have structured types. We have maps, records, maps, arrays, and structs. There should be nothing new for you because this is all covered a few weeks ago, right? You already know all of that. I'm just saying in the case of data frames in Spark, this is the types you have. And I even prepared this for you, which is to show you in Java and in Python, what is the equivalence for all of these. This is Java, this is Python, and this is JSONic, but it's also XML schema, it's also JSON. You know, these are all the same types that we'll also see when we study in a few weeks JSONic. So you see, you have a correspondence between the types on all sides. You see that the decimal is a bit tricky because you need to define the precision and the scale. If it's an integer, basically it's a scale of 0, but still using the decimal type, because here all you have is this limited size byte, short, int, long, right? Here it's a precision all the way to 38. I think it's digits, not entirely sure, but a precision of 38. So it's a big decimal in Java. In JSONic, you have a distinction between decimal and integer, right? Okay, so these are the types. But again, that should be a very low cognitive load for you because we've covered that a few weeks ago and you already know the landscape. The only thing is that it's then read the documentation. You just need to remember the names that might be different from language to language, right? But you can, depending on your taste, if you prefer Java, you can look at the Java column. If you prefer Python, you can look at the Python column. Okay, who is comfortable with that? Right, that should be relatively straightforward. And these are the complex types where you have arrays, maps, and structs, which in Java map to lists, maps, and rows. So the struct is the row, the same row that you have in your data frame, it's just nested. In Python, we have lists and dicts, and in JSONic, we have arrays and objects, which is just JSON, right? JSON arrays and JSON objects. Okay, Now the data formats, it's super easy. Just say Spark read JSON, Spark read Parquet, Spark read CSV, Spark read text, JDBCs for connecting to PostgreSQL or a relational database. And for other formats, it's actually a plugin system that anybody can add new formats. And the generic way is to just specify with the format functions or Avro or whatever, then loading the data set. So you see, in one line, you can load any data set and you get a data frame out of that. And then you can write Spark SQL and then collect the results. It's that simple. There are also ways that you can do some mappings between Java classes and schemas, but I'm not speaking too much about that. But then you can actually replace row with a Java class if you do that sort of things. But again, that's something that I'm just mentioning en passant. Okay, so now we've done the SQL brush up. So you know about SQL, you know how it works. In particular, select from where, group by, having, order by, limit, offset. This is something you have to know by heart. Okay, so SQL or transformations. What's going to happen is that behind the scenes, when you create these data frames, Spark is automatically going to create RDDs in the background for you, but in a more efficient way. And it's going to map your logical plan with transformations on data frames or SQL. And it's mapping into a physical plan on these RDDs. But this is all hidden from you. This is the physical level. You don't even need to know or care about what's going on here. Because we have this whole pipeline of optimization, there is an optimizer called Catalyst that is used in the case of Spark SQL and data frames. And all you need to care about is your SQL query and your data frame. All the rest is automagical, just happens, and it will figure out the best way to execute for it. Okay, let's look closer to the dialect because you know it's very close to what you know. Select from where, group by, having, order by, limit, offset. No, actually, there's no offset. This is sadly, I'm very sad about that. I wish they actually had implemented offset, but you don't have offset in Spark SQL. Okay. So you can take the first 100, but you cannot paginate or take the other ones. Well, actually you can. It's just that you need to look it up on Stack Overflow and copy paste the 20 lines that allow you to do that. It exists. We actually did it in RumbleDB. We credit, of course, whoever did that. But yes, offset is very, very complicated to actually get. Okay. Order by. Now, Spark SQL has a few more things than standard SQL. It has a sort by. Now you're going to tell me what's the difference between sort by and order by, right? That sounds very much the same. Well, the difference is that order by is a real order over the entire table, the entire data frame, I should say data frame rather than table. Sort by is only sorting in every partition, in every task, right? It's not sorting across partitions. So you need to understand that sort by is a very physical thing. In fact, as a database query language researcher, that hurts because this is very physical, but sometimes you might need to control a bit more on the physical level and really specifically sort within each partition. The reason it hurts me is that in order to understand this, you need to be aware of the partitions. Here, you don't. If you have just order by, you don't care about partitions. It's all hidden. Here, the partitions are visible to the user when you do that, right? I can imagine that for some people it can be useful. So here it is, you can sort by. There is also a distribute by. This also hurts me because this is something that makes you partition aware that normally with data independence you shouldn't see. But again, some people might need it. This creates the partitions. This is basically saying, please repartition my data frame in such a way that each country, all the same countries are in the same partition. Right, so France is all in that partition, Germany is all in that partition, India is all in that partition, and so on and so on. Okay, so this is distribute by, and you can use both distribute by and sort by. Distribute by and sort by can be shortcut as cluster by. Cluster by is kind of an unfinished order by, right? It's like order by, except that you haven't merged all of the sorted partitions. So let's call it, it's the first half of the merge sort. Let me put it that way, right? Cluster by is the first half of the merge sort. Okay? So I wanted to mention them again from a data independence perspective that exposes the physical layer, but here they are, sort by, distribute by, and cluster by as a sugar for distribute by, sort by. Okay? What you also need to understand, now I'm getting back to my comfort zone with things that do not expose the physical level. Group by is going to shuffle, order by is going to shuffle. So here you're going to have two shuffles, but in fact, you can probably guess that it's going to be just one shuffle. Why? Why don't you need the second shuffle? Can you figure it out? Yes? Could we have the catch box?
Because we group by and order by the same thing.
Exactly. We group by and order by the same thing. It means that after the group by, the partitions are already country friendly. So when you order by, it's already on the same partitions. But you probably still need to do the second part of the merge sort. So now that I'm thinking out loud, you might still need a shuffle for completing the merge sort. Okay. Now, I told you that it's data frames. It's more generic than relational tables in two ways. It can be nested. It can have nested objects and it can have nested arrays. For example, here, I have something that normally I wouldn't have in a standard relational database. I have in the third column an array of strings. That's my type. It's not atomic. It's not the first normal form. I have arrays of strings. So what do I do with that? Because SQL doesn't speak array of strings, right? SQL normally uses the first normal form, right? So there's an extension of SQL that is in Spark SQL that allows you to manipulate these arrays. And there is in particular this explode function acting on the countries column that's going to open the arrays and duplicate these values here as many times as there is a value in the array. For example, here I have Einstein D, Einstein I, Einstein CH, and so on, and you just duplicate the rows here. This is the explode function. Okay, so you basically just fit everything in a table every time. This is an equivalent syntax called the lateral view. You can view it as a self-join. You're basically joining the first two columns with the third column seen as another table. It's called the lateral view. Right? This is even more complex because here we have an array of objects. So we create a lateral view with the continents and a lateral view with the countries, and then get that other table over there. So you see, we can extend SQL in order to deal with nestedness. For objects, it's the same with dots. So if we have JSON objects in there, we can extract the first and the last in columns with the dots. Who finds that very complex? Who finds that super easy? Wow, some of you find it super easy. I find it complex. Especially imagine this with a depth of 20, an array, an array, an array, an array, an array. Okay, so you need to understand that this takes care of some of the nestedness. In simple use cases, you can deal with nested arrays and nested objects if it's simple enough. We'll see later that for more complex use cases, this is getting too verbose and too complex, but fortunately, there are solutions to that we will study tomorrow and then in the next week, right? There are better ways to deal with this nestedness. Okay. So the limits of data frames are the heterogeneity, because imagine that in your data set, it's not valid. Here you have an array of integers rather than an integer. If you try to read it in Spark, it will actually work. It will just hit it with a hammer until it fits in a data frame. That's what I told you earlier. How does it hit it with a hammer? Where it's going to say, okay, well, this is not the same type. Let's put everything in a string. So it's creating this string column over there, and everything is dropped as a string. This string is just a serialization of JSON. So this is the string 1, the string 2, the string square bracket 3, 4 square bracket, and so on. What did you just do? You basically make it the user's problem. Right? Spark is making it your problem to deal with. Now you're going to have to yourself parse that again, and in particular distinguish between array and integer. This is a limitation. So you need to be aware of these limitations. If your data is like this is going to be much more complex to handle in the data frame way. Okay, but I'll come back to these limitations and show you solutions for the cases where the data is, that's called messy data. Okay. That's my final slide of Spark, where you can see that you can go back and forth between RDDs and data frames, right? You can turn. Oh, I see why you're moving. It's fine. So you can turn RDDs in data frames and data frames about RDDs. But you know, it's 5 and that's the last slide. So that's good, right? So thank you very much. This completes today's lecture. And I'll see you tomorrow. And tomorrow we'll start document stores with MongoDB, starting looking into how to query messy JSON. Thank you very much for your attention. And I'll see you tomorrow at 9 for the continuation.